Section: Introduction. In this section, we explore the learning capabilities of transformers in handling tasks involving large amounts of text, image, or audio data. While transformers excel in some reasoning tasks, they struggle with more complex tasks like logic or mathematics that require combining learned concepts to make inferences. We aim to understand why current transformer-based models face challenges in learning at scale for such tasks. We begin by discussing syllogism composition, which involves inferring new knowledge by combining existing knowledge efficiently. For example, inferring A, right arrow C from A, right arrow B and B, right arrow C is a basic form of reasoning. We want to determine if a syllogism can be composed from prior implications, which can be represented as identifying paths in token sequences describing directed edges in a graph. When faced with tasks like syllogism composition on a graph with randomly drawn edges, transformers struggle to efficiently learn. We investigate a binary classification task involving graphs with different structures to understand when transformers can effectively learn. The complexity of learning increases exponentially as the size of the graph grows, and even large transformers with millions of parameters struggle to learn the task for certain graph sizes. The cycle task, which involves determining connectivity in graphs with specific structures, poses a challenge for transformers due to the need for global reasoning. Unlike tasks with clear patterns in input representations, the cycle task requires considering a large number of input tokens for accurate inference, making it difficult for transformers to handle. Tasks like subset parities also present challenges for transformers due to the requirement for global reasoning. While some tasks can be proven to be inefficiently learnable by regular neural networks, the cycle task remains challenging for transformer-like models. We aim to develop a general complexity measure to explain why such tasks are hard for transformers and explore how Scratchpad methodologies can aid in overcoming these challenges. Our key questions are: 1. How can we formalize the concept of a local reasoning barrier in general terms? 2. Can Scratchpad methodologies help in breaking the local reasoning barrier for transformer models? Section Summary. In this section, we explore the challenges transformers face in tasks requiring advanced reasoning, such as syllogism composition and the cycle task. While transformers excel in learning from vast amounts of data, they struggle with tasks that demand complex reasoning and global understanding, as seen in the cycle task where even large-scale transformers fail to efficiently learn due to the absence of low-complexity patterns in the input representation. This highlights the need to develop a comprehensive complexity measure to understand why such tasks pose a local reasoning barrier for transformer models and investigate how Scratchpad methodologies could potentially overcome these challenges. Section: Our contributions. In this section, we present our contributions. We introduce the concept of distribution locality to determine when transformers can efficiently achieve weak learning. Distribution locality quantifies the minimum number of tokens needed, in addition to the token histogram, to significantly correlate with the target. It is linked to correlations with NC-0 circuits, highlighting the difference between learnability and TC-1 control. Our results based on distribution locality include a conjecture stating that a regular transformer can efficiently achieve weak learning only if the distribution locality is constant. We also prove the locality barrier in a specific variant of the cycle task under certain conditions. The cycle task serves as a simple benchmark to assess models' global reasoning abilities. To address the locality barrier, we introduce two types of scratchpads. The agnostic scratchpad extends the concept to cases where a polynomial-size scratchpad is used without supervision. This shows that efficient weak learning is not possible if the locality is not constant, requiring some knowledge about what to learn in the scratchpad. The educated scratchpad introduces the idea of autoregressive locality to determine when an educated scratchpad can break the locality of a task with lower locality subtasks. Experimental results show that educated scratchpads with constant autoregressive locality enable transformers to efficiently learn tasks with high locality initially. This provides a measure of how beneficial a Scratchpad can be in breaking down a complex task. We also define the inductive Scratchpad, a type of educated Scratchpad that leverages induction. For tasks like the cycle, arithmetic, or parity tasks that allow for an inductive decomposition, the inductive Scratchpad improves both locality and out-of-distribution generalization compared to fully educated Scratchpads. This leads to significant improvements in generalization for additions and parities. Furthermore, we discussed the local reasoning barrier in prior literature, focusing on complexity measures relevant to regular transformers trained by SGD and fixed data distributions. Despite existing measures like noise sensitivity and NTK alignment, finding a simple measure for transformer weak learning remains unresolved. We then define distribution locality and autoregressive locality to quantify the locality barrier and its relevance to efficient weak learning of regular transformers across various data distributions. Section Summary. In this section, we introduce the concept of distribution locality to determine when weak learning is efficiently achievable by transformers. The distribution locality quantifies the minimum number of tokens needed, in addition to the token histogram, to correlate significantly with the target, providing a precise measure applicable to data distributions without requiring orbit arguments. Our results suggest that efficient weak learning by a regular transformer is possible only if the distribution locality remains constant, as demonstrated through a conjecture and a theorem on the locality barrier in specific tasks like the cycle task. Additionally, we explore the use of Scratchpads, distinguishing between agnostic and educated Scratchpads, and introduce the notion of inductive Scratchpads that leverage induction to break task locality and enhance out-of-distribution generalization, showcasing significant improvements in tasks like additions and parities. Section. The locality has the attributes that of being, I, a fairly explicit measure, E, applicable to any data distribution on tokens without having to infer a distribution class from the model invariances to estimate the distribution complexity, E, not limited to I, D, inputs but any input distribution, IV, relevant to current models of interest such as transformers. In particular, back to the cycle task, we have that any set of $n-1 edges have the same distribution in class 1 or 2, therefore the locality is at least $n. We have $loc, $cycle task $gen. As discussed in the next section, this explains why the cycle task is hard to learn. In contrast, the example at the beginning of section has a much lower locality, as being connected correlates to query nodes having large enough degrees, and thus it can be expected for the model to learn with non-trivial accuracy, e.g. using degree shortcuts. In this section, we will discuss the characteristics and examples of locality. Locality is defined by several attributes. It is a clear measure, can be applied to any data distribution without needing to determine a distribution class, is not restricted to specific input distributions, and is relevant to models like transformers. For instance, in a cycle task, if any set of n1 edges has the same distribution in class 1 or 2, then the locality is at least n. This explains why the cycle task is challenging to learn. On the other hand, in a different example, the locality is lower because the correlation between connected nodes and their degrees makes it easier for the model to learn accurately. Transformers require low locality according to formal results. A neural network is considered T-regular if it meets certain criteria, such as being a transformer of polynomial size with specific embeddings, weights, and attention mechanisms. A T-regular network with a Scratchpad involves a constant-sized token alphabet and performs computations on sequences. Regarding learnability, we focus on descent algorithms in this paper. We investigate the ability of transformers to compute target functions with certain limitations. Transformers with constant alphabet size and limited accuracy are shown to be restricted in the functions they can compute. The conjecture suggests that a distribution is efficiently learnable by a T-regular transformer only if it has constant locality. Additionally, the learning model's symmetry under permutations of inputs is crucial for understanding the behavior of the model. By using causal masking or specific positional embeddings, transformers can focus on subsets of inputs and potentially learn functions with higher locality. For example, certain positional embeddings can help the transformer learn functions that would otherwise be challenging. Lastly, a specific graph generation process is described to illustrate how training a T-regular neural network on generated data may result in failure to learn effectively. Section Summary. In this section, we explore the attributes of locality, which include being a clear measure applicable to various data distributions without needing to infer a distribution class, relevant to models like transformers, and not restricted to specific input distributions. We find that the cycle task's difficulty in learning can be attributed to its high locality, while tasks with lower locality, like those involving connected nodes, may be learned more easily by models. Additionally, we define T-regular neural networks and discuss their limitations in computing functions based on their depth and scratchpad size, shedding light on the challenges posed by the locality barrier for efficient learning. Section. Agnostic scratchpads cannot break the locality. In this section, we examine how agnostic scratchpads cannot break the locality. We consider training a neural network with a scratchpad to learn a specific task using a stochastic gradient descent algorithm. At each step, we randomly select a sample and compute the scratchpad's value based on the input. By adjusting the scratchpad's entries and calculating the loss, we update the network using the gradient. We find that a well-behaved probability distribution can be efficiently learned by a neural network with a scratchpad if the task has constant locality. This concept extends to transformers as well. Previous studies have shown that incorporating scratchpads in transformer models can improve learning outcomes across various tasks. By providing models with an educated scratchpad, we can enhance learning efficiency, especially in autoregressive settings. We illustrate how designing scratchpads with low locality can aid in learning tasks effectively, focusing on examples like parity functions and the cycle task. For instance, when learning parity functions, which are known to be challenging, using a scratchpad with intermediate targets can simplify the learning process. Similarly, for the cycle task, a scratchpad that follows a depth-first search algorithm can significantly reduce the task's locality, making it easier to learn. By breaking down complex tasks into simpler sub-targets using scratchpads, we can facilitate efficient learning and develop useful representations. Overall, scratchpads play a crucial role in enhancing learning efficiency by managing the locality of tasks. While theoretical works explore advanced applications like emulating Turing machines, practical implementations often focus on devising more general scratchpads to support various reasoning tasks, emphasizing the importance of inductive learning steps for improved performance. Section Summary. In this section, we explore the concept of scratchpads in neural network training and their impact on learning efficiency. By breaking down complex tasks into simpler intermediate targets, scratchpads can reduce the locality of learning, making it easier for models to efficiently learn sequences like parity functions and cycle tasks. For instance, using scratchpads with low locality, such as the cumulative product scratchpad for parity tasks or the DFS scratchpad for cycle tasks, can significantly improve learning outcomes by enabling models to focus on smaller, more manageable steps in the learning process. Section. Inductive scratchpads. In this section, we explored the concept of inductive scratchpads. We found that scratchpads, when fully educated, can struggle with the number of reasoning steps, leading to poor generalization outside the known data. To address this issue, we introduced the idea of inductive scratchpads, which can be applied to various reasoning tasks. When scratchpads are fully educated, they may become too specialized in handling the training data, resulting in poor performance on new, unseen data. For instance, in a cycle task with 40 nodes, we observed that the model excelled on the training data but failed to generalize well to different scenarios during testing. Inductive scratchpads offer a solution to this problem. In many reasoning tasks, including graph algorithms and optimization algorithms, we can iteratively apply an operation to a state variable to compute the output. This iterative process can be captured by an induction function that updates states step by step until a termination condition is met. By using attention masking and reindexing token positions, we can encourage the desired inductive behavior in models. The inductive Scratchpad format includes special tokens like <start greater than to separate the question from intermediate states and state greater than to mark state transitions. This modification helps the model focus on the most recent state for each new update, promoting better generalization and learning of the induction function. Overall, the inductive Scratchpad enhances the model's ability to generalize beyond the training data, improving performance on tasks like the cycle task, parity, and addition tasks. This approach can be seamlessly integrated into existing language models without affecting their performance on other tasks. Section Summary. Inductive Scratchpads. In this section, we introduce the concept of inductive Scratchpads to address the issue of poor out-of-distribution generalization observed with fully educated Scratchpads. Inductive Scratchpads are designed to promote induction by focusing on generating new states based only on the last state, improving OOD generalization in tasks like the cycle task, parity, and addition tasks. By using attention masking and reindexing tokens, the inductive Scratchpad facilitates learning the induction function and can be seamlessly integrated into existing language models without affecting their performance on other tasks. Section: Inductive Scratchpad for the cycle task. In this section, we created an inductive Scratchpad for the cycle task using the DFS algorithm. By treating each step of the DFS algorithm as a state, we transformed the DFS Scratchpad into an inductive one. This inductive Scratchpad keeps track of the current node in the DFS process. We demonstrated that this inductive Scratchpad can handle more reasoning steps than those encountered during training, allowing for out-of-distribution generalization when the distance between nodes is increased. We also explored how inductive Scratchpads can facilitate length generalization for tasks like parity and addition. For the parity task, we introduced random spaces between bits and designed an inductive Scratchpad based on the bit positions to compute parity iteratively. This approach enabled training a transformer on up to 30 bits and achieving generalization on up to 50 or 55 bits. When it comes to the addition task, we considered two formats for inductive Scratchpads. One format involved inserting random spaces between digits in the input and using digit positions to compute addition step by step, similar to the parity task. With this method, we could generalize to numbers with 20 digits while training on numbers with up to 10 digits. In the other format, we used random tokens in the input and computed addition by shifting operands digit by digit. Although this format allowed generalization from 4 to 26 digits, it resulted in a less natural input format. Results for different seeds are presented in the figures, and more details about these Scratchpads can be found in the appendices, along with a comparison with recent methods.